Good afternoon, evening, my dear students, because it's exactly 4 o'clock. So I can call it good evening also, and I can call it good afternoon also. So welcome to this session. Today, we are going to do thermodynamics. Now, thermodynamics is an extremely important chapter. It has not been deleted, it has not been restricted, it has not been eliminated, it has not been reduced. And thermodynamics is entirely there. So, this is an important chapter where you get the information about the entire reasons of the reactions. So we are going to begin today with thermodynamics. I know that you have certain problems with thermodynamics, and thermodynamics is a little easier as compared to equilibrium, or maybe a little bit more difficult as compared to equilibrium, because the equilibrium chapter is also thermodynamic equilibrium. So we are going to do this chapter quite in detail, quite nicely and thoroughly. So, welcome to this session. Like, subscribe, share and comment. So, like the session, subscribe to the channel, share it with your friends and comment what you liked and how it can be improved. So, let's begin over with it. I believe you are able to hear me and see me perfectly clearly. Fine. So, here we have the thermodynamics, and today we are going to talk about the various terminologies that we use in thermodynamics chapter. Begin. Great. So, a little bit about myself. My name is Anoop Vashishtha. I'm an MSc in chemistry from University of Delhi. 26 plus years of teaching experience, and that is very much clear by my hair. I have some, okay, and lakhs of students have been taught by me. So, to begin with thermodynamics, we are not going to waste any more time. We are going to straightforward begin with thermodynamics. Whoever is missing the class, be sure to cover it up. Now, to begin with a word called thermodynamics. Now, I am going to go, whenever we have the slides with us, the speed actually increases a bit because I am not writing anything. So, I am only reading it. So, you need to be careful and you need to control my speed. If you have any problems you have, just ask me the question. We have very few students in the class, and remember, tomorrow we are having marathon sessions of electrochemistry and thermodynamics. So, tomorrow we are going to have two sessions, one of electrochemistry, one of thermodynamics, 3 hours each, 11 to 2 and 4 to 7. So, we have two sessions going on tomorrow, and today in the evening at 8:30 p.m. we are having the session of the questions of surface chemistry. Today I have around 45 questions, so I believe we would be able to do them in 1 hour. Surface chemistry. Remember, although this chapter has been eliminated from 12th class CBSE, this chapter is an important chapter for the NEET examination. Clear? Today at 8:30 p.m. we have already finished off the surface chemistry in the marathon classes. Welcome. Clear? So now when we talk about thermodynamics, thermodynamics is a part of science which tells us the feasibility. Feasibility, you may call it the possibility. Quite obviously, if the possibility was the right word, we would have used the word possibility only, not feasibility. Feasibility can be loosely translated into possibility. Feasibility means whether it can happen. That is what we call as the feasibility. Something like whether you will be able to wear a particular trouser or not. Will you be able to? You want to wear it, it's a different case. You will wear it in future, that's a different case. I'm just saying whether you can wear it. That is the feasibility, possibility. Possibility is little different, so we are not going to translate it right as a possibility. So it is feasibility of a process. I'm not even saying reaction, I'm saying process. The process could be a physical process, it could be a chemical process, it could be a normal process. So thermodynamics talks about the feasibility of process. It predicts whether the reaction can take place, and that too under a given set of conditions. It is something like, are you going to wear a trouser? Now, Are you going to wear a trouser or will you be inclined to wear a trouser is not only dependent on whether the trouser fits you or not, it also depends on what the occasion is. Are you going to wear a trouser while going deep sea diving? Are you going to wear a trouser while you are doing yoga? Are you going to wear a trouser while you are in a party, and depending on which kind of party it is? So, feasibility is not just something like that it is going to take place. Feasibility also depends on what the situation is. One thing which is feasible under a given set of conditions might become non-feasible or non-spontaneous under different set of conditions. So, conditions need to be defined whether it can happen or it will happen or not. Okay, so that is why even given set of condition becomes important. And if at all the process takes place, what kind of energy transformation we can expect from it? Means if it happens, like where you wear the trouser, are you going to throw a tantrum? Do you need to be bribed to wear it, or you are going to pay to wear it? So that is what we have as the kind of energy transformation. So this is what we talk about the way. So this is what we have as thermodynamics. So the branch of science which deals with different forms of energy and their interconversion, it deals with matter and bulk. Thermodynamics is a macroscopic property. Means thermodynamics does not talk about the individual particles, it talks about the collection of particles. It talks about the huge measurable properties. It's not going to talk about atomic structure, rather it's going to talk about the collection of atoms. So that is what we have as thermodynamics. 9 PM Sachin sir का special class है. Oh, clash. Can't help it. Okay. These need to be smooth. We'll have the. चलो आज का clash हो गया. Let's see. But 8:30 to 9 you are going to be there, isn't it? Clear? So you can have a little bit of delay in Sachin sir's class. 8:30 to 9 you are going to be there. Fine enough. Okay. The properties associated with bulk are called macroscopic properties, and thermodynamics deals with macroscopic properties. Now we need to study thermodynamics. What exactly we are going to know? What drives a chemical reaction? What makes the chemical reaction possible? Energy changes involved in a chemical reaction, extent of the completion of the reaction. Yes, equilibrium. Equilibrium is a part of thermodynamics. And then the criteria to predict the feasibility of the process, whether the process can take place in a given set of conditions or not. Clear? Now these are the objectives. Now to predict the feasibility of a given transformation, whether it can take place or not, to derive the various energy changes taking place during a given change and interrelate them, and to present the experimental data in a systematic order, to derive at what condition the equilibrium is attained. So it is going to talk about the conditions under which we are going to attain the equilibrium. Fine enough. So I believe you all have registered for the class, that is special class today. Go ahead and register for the special class, and if you have not already done the downloading of the app, go ahead and download the app using the code AVLive. Fine. So here you can derive the what condition the equilibrium is attained by a change. Now what are the limitations of thermodynamics? Sometimes people think that thermodynamics, once we know thermodynamics, we will be able to tell everything. If we know the energy change in the reaction, we will be able to tell everything. No, it is not true. Thermodynamics has many limitations. In fact, these limitations are overcome by the topic called kinetics, and the limitations of thermodynamics are the things which kinetics deals with, and the limitations of kinetics is the one which thermodynamics deals with. Thermodynamics and kinetics are complementary to each other. When you join them together, they make it a whole, complete. So, what is the limitation of thermodynamics? It can only predict whether the given process, including a chemical reaction, is feasible under a given set of conditions or not. Whether it can take place or not. It does not tell anything about the rate at which a given process may proceed. Please remember, many times I ask a question that a reaction is releasing out 1000 kilojoules of energy, and another reaction is absorbing 50 kilojoules of energy. Which is faster? Everybody has a tendency to say that the reaction in which 1000 kilojoules of energy is being released out is going to be faster, while the reaction in which energy is being absorbed is going to be slower. No, you cannot predict it. The energy being absorbed is the evaporation of water. The energy being released out is combustion of coal. And you keep both the things at, let us say, 100 degrees Celsius. When you put them at 100 degrees Celsius, then in that case, evaporation of water is going to be very fast, although the coal is not going to even change. So the rate of reaction of evaporation is going to be much faster, although it is endothermic and it is absorbing energy. While the combustion of coal, which is an exothermic reaction and it is releasing energy, that is not even going to take place. So please remember, thermodynamics can never predict the rate of reaction, the speed of reaction. Is this clear? Okay. Now, it concerns itself only with the initial and final state of a system and tells nothing about the mechanism or the path followed. Something like, I want a person to wear a trouser. I'm only bothered about, okay, this time, this place, he's not wearing the trouser and now he is wearing the trouser. I'm not bothered how he did it, whether he put the left foot inside first or the right foot inside first, or he put both the feet inside it. I don't care. I only bother about that he was not wearing a trouser and now he is wearing the trouser. That's it. That is thermodynamics. Further, the laws of thermodynamics apply to behavior of assemblies of a vast number. It is a bulk property. It is dealing with the huge number of particles, not with a limited number of particles and not with individual molecules. So it is not bothered with the same one kind of molecules. Lord Punnett, ठीक है, समझ गया मतलब? Whoever has not liked, just like the session. It fails to explain about the systems away from equilibrium. That is, the systems which are actually moving, thermodynamics cannot tell anything about it. So systems which are at equilibrium, that is, they have reached a certain stable state, thermodynamics only talks about that this is the change from here to here. Very clear? Okay, so these are the limitations of thermodynamics. And thermodynamics cannot tell whether the reaction will take place or not. You can jump from a window. Yes, you can jump from a window. That is feasibility. That is thermodynamics. But will you jump? What would be the condition under which you are going to jump? That is kinetics. Clear? Now, to understand and study thermodynamics, there are certain prerequisites. Prerequisite means that you need to understand certain terms, certain things you need to know. It is something like, okay, to get the admission in NEET, you need to clear your board examination with certain percentage. That is a prerequisite before you even attempt to clear the NEET examination. So that is what we call as prerequisites. Remember, I am teaching you all the questions, all the words also. I am not here considering that you know absolute English. I am not considering that you know absolute chemistry. I am not teaching to the toppers here. I want to teach to the people who want to become toppers. And they know that at this moment they need to learn. If anybody is here who believes that they know entire chemistry, this class is not for you. This class is for the people who want to learn chemistry and in the process they want to understand English as well. So I am going to teach in a very simple language and explain each and every word. So these are terminologies, the words of thermodynamics. So let's begin over with the words of thermodynamics. So these are the terms used in thermodynamics. The thermodynamics word itself, system, surrounding, boundary. Let us understand what each of these terms mean. Let's begin over with it. So your copy pen is ready. So you are ready to take the notes. System, the part of the universe under observation or thermodynamic investigation. And there is one more word, having definite boundary. We are going to have it in detail even more. It includes everything else in the universe other than the system, that is surrounding, and the boundary is the real or imaginary layer separating the system from its surrounding. So boundary defines the system and the surrounding. It allows us to control and keep track of all the movements of matter and energy. Okay. Now we have something called the types of boundaries as well, but we are going to do that whenever we are going to do the questions of thermodynamics. So now what is universe? Universe is system plus surrounding. Please remember, the boundary itself is a part of surrounding, it's not the part of the system. Okay. So we have the universe. System plus surrounding is the universe. Now let's define what is system exactly. System is the part of the universe. Quite obviously, it is going to remain in the universe. Universe is including everything. So system also be part of the universe only. System is the part of the universe having a definite boundary. Now this definite boundary could be real or could be imaginary. I could just simply say a coordinate system. Let us say we have a coordinate system, or we have something like latitude and longitudes. Latitude and longitudes are imaginary lines. They are not somewhere drawn on the surface of the earth. They are just imaginary lines, and we have considered a reference from which we are talking about longitudes and latitudes. Isn't it? So these are imaginary lines. In the same manner, we can have imaginary boundaries. We can simply make a Cartesian coordinate. We can have an origin, and with respect to the origin, we can have a system being defined. So remember, so these boundaries could be real, could be imaginary, could be conducting, could be insulating, could be porous, could be non-porous. So there could be very many kind of boundaries. Is it clear? So these boundaries may be real or imaginary, but they have to be there. Otherwise, I cannot define the system. Clear? So what is a system? That is absolutely clear. Then we have surrounding. Everything other than the system, which includes the boundaries as well, is surrounding. Clear? So that is what we have as the surrounding. I hope I am not going fast. I am explaining everything. I am making it absolutely clear. Anybody has to ask anything, go ahead and ask it. Now, this is a term which is normally missed in the book, but they are actually talking about this is the immediate surrounding. What is the immediate surrounding? Let us say I have this particular cup. This cup contains water. Now this water is capable of exchanging energy with the air in this particular studio room. The studio room has an insulating door. This door practically seals the person inside. And when the person is sealed inside, then in that case, I don't have any connection with the person outside. So for all purposes, practical, logical, ethical, whatever purposes might be, the surrounding of this glass of water is this room. Should I take the entire universe as the surrounding? No, no use taking the entire universe as the surrounding, because universe is not being disturbed by this particular system. So the part of the universe which is actually in a position or in a condition to interact with the system, whether it is able to exchange energy, whether it is able to exchange matter, or it is able to exchange both, that part of the universe is immediate surrounding. Any change in the system, exact equal and opposite change takes place in the immediate surrounding. So we can actually find out the change in the system by finding the change in the surrounding. That is what we call as immediate surrounding. Whenever we are actually talking about surrounding in thermodynamics, we are referring to immediate surroundings only. Many a times the reaction is taking place in a water bath. That water bath becomes the immediate surrounding, and rest of the part we are not even bothered about. Clear? So that is what we have as the immediate surrounding. Okay? Clear? So most of the cases we are talking about immediate surrounding. Now let us say we have boundary. Boundary is anything which separates the system and surroundings. That is called a boundary. That is, we refer to the boundary to define the system and the surrounding. This is the boundary. So inside it is the system, outside it is the surrounding. It could be other way around also, as we define it. So it's called envelope, it's called a wall. This envelope may be imaginary or real, I just told you. It may be rigid or it may be non-rigid. Non-rigid could be flexible. That is, I have a movable, massless, frictionless piston so that the system can expand. I am having a balloon. If I put the air in it, then in that case the balloon expands. The boundary is expandable. It is flexible. Or it could be rigid. I have a rigid container which whatever I put in, the volume of the container does not change. So that could be a rigid container. It may be a conductor of heat, which we call as diathermic wall. Or it may be a non-conductor, insulator. That could be called an adiabatic wall. It could be porous or it could be non-porous. Porous would allow the matter to pass through it. The non-porous would not allow the matter to pass through it. Is that clear, Prerna? Yes. Non-rigid, expandable, flexible, whatever the word you want to use. Any confusions, anybody? Okay. So that's what we have as the wall, adiabatic wall. And then we have a term called process. See, these words are normal English language words and they mean what they actually mean. We are not changing the meaning of it. Process is any operation, anything by which a change is brought about in the system. We are observing the system, we are investigating the system, so obviously we are going to talk about the change in the system. So that is what we call as a process. Any doubts, anybody? Vivek, polar, non-polar are the conditions. Why are we talking about polar and non-polar in this case? Process is an interaction of the system with the surrounding. And depending on this interaction, how the system can interact with the surrounding, the systems are classified. Systems are classified in various ways. Depending on that, we are talking about the classification. So, let's classify the system based on interaction of the system with the surrounding. Please remember, a system is actually defined by the process which is taking place in it. If I have this water container, although I don't have a lid over it, there is no lid over it, but if the volume and the mass of the water is not changing, it will be defined as a closed system because mass remains a constant. Now it is not a closed system, now it is an open system. Let's define the systems. Okay, Nishu, what's the problem? No, sir. First of all, we talk about a phase. Phase is defined as a homogeneous and physically distinct part of the system, which is bound by a system and is mechanically separable from the other parts of the system. Okay, phase. Sometimes people call the phase as a state, but actually, whenever we have different states, there are different phases always there. But many times it happens that we have the same state, but still there are different phases. Like you put kerosene oil and water. If you talk about kerosene oil and water, then in that case, if you take kerosene oil, the kerosene oil is going to show one layer and water is going to show another layer, and kerosene oil will be above water. So this is going to be kerosene oil. You can actually see a boundary between them. So when we see a boundary, we are able to distinguish between the two parts. We are talking about the different phases. Okay, wherever we are able to distinguish the parts visually, it is different phases. Within a phase, they have the same density, intrinsic properties are all same. The same temperature, same pressure, that's what we have as same phase. Anyone has any confusions here? Whoever has not liked, just quickly like it. So that's what we have as the phase. Now, based on the interaction of the system and surrounding the system are of four types. Generally, the books say only 3 types of systems. Every book, in fact, says 3 types of system. I prefer to call 4 types of system because we have 4 types of processes. Clear? The very first, the open system. The system which exchanges mass and energy. Remember, when there is exchange of mass, rest assured there is an exchange of energy also. You cannot exchange mass without exchanging energy. So even if I say where there is exchange of mass, that would be enough to say. But still we say mass and energy. with the surrounding, that is the system in which there is a change in mass, is known as an open system. Even if there is a change of mass for a fraction of a second, fraction of a moment, still it will become open system. Okay? An open system has porous boundaries, that is, matter can be exchanged. In this case, mass is a variable. So any process, any system where you say that you are not able to say that, okay, mass is a constant. Please remember, in chemical processes, moles can vary even if mass remains the same. In physical process, mass constant means moles remain constant. Is it clear? So in physical process, mass and moles, they are constant. Anyone has to ask anything? Any kind of doubts you have? So that is what we have as mass becomes a variable in an open system. Remember, many of the systems which we find, like any living organism, if the organism is living, it's an open system. Remember, any living organism. Clear? So, a system which exchanges energy but not mass with the surrounding, in this system, mass remains a constant. That is what we have as a closed system. So, closed system is basically defined as keeping mass constant. Whenever the mass remains a constant, it's a closed system. In addition to that, it might be another system as well, but then in that case, it's a closed system. So, closed system is where the mass remains a constant. It has conducting boundaries. That is, it is exchanging heat and energy. So that's what we have as a closed system. Identifying feature, mass remains a constant. Okay? And then we have an adiabatic system. Now this is a system which is not normally defined in the books. It is a thermally insulated system. So adiabatic system does not allow the movement of heat. And quite obviously, if it is not allowing the movement of heat, the movement of mass also is not taking place. But it still can exchange energy in the form of work. That is, you can actually increase the temperature. Let's say this is an insulated bottle. If it is an insulated bottle, I can actually increase the energy of the system. I can increase the temperature of the substance inside this container by shaking it. So if I shake it, I actually give it energy and it can actually increase the temperature. It will increase the temperature. You might have used the mixies, the grinders. What happens in the grinders? You are grinding the dry things and it becomes quite hot. So that is what we know as the temperature, the thermally insulated system. It exchanges energy in the form of work, but exchange of heat does not take place. Nishu, it's not necessary that mass remains mole constant. No. Even if mass remains a constant, if we have a chemical process, the moles may not remain constant. Something like, let us say we have a closed container in which we have some amount of NH4Cl, ammonium chloride. Now this ammonium chloride, if it is heated, it is capable of converting into NH3 and HCl. Now here it is 1 mole. Here it is 2 moles and the mass remains constant. But remember, this is a chemical process. Not for physical process. Physical process, whenever the mass is remaining constant, the moles remain constant. Is this clear, Nishu? Your question has been answered? Okay. So that is what we have as adiabatic system. Adiabatic system, the heat is not being exchanged. The mass remains a constant. It's a closed system with thermal insulation. But the energy can be exchanged in the form of work. And then comes isolated. Isolated system, we can actually practically say that it does not have any surrounding because it's not interacting in any way with the surrounding. The mass remains constant, the energy remains constant, there is no exchange of energy, any form, or the exchange of mass. So that is what we have as the isolated system. Clear? Isolation simply means no interaction with anything. So isolated system practically can be said is a system without any surrounding, or the best example of the isolated system is the universe itself. Clear? So these are the systems: open, closed, isolated system. Open system, matter can exchange, heat can exchange. Closed system, heat can exchange but not the matter. Isolated system, heat, energy, no exchange is taking place. A thermos flask, an open beaker. Clear? So that's what we have as open, closed and isolated. Any confusions, anybody? So, which of the following is an example of an open system? A human body, the earth, pond, all of these? Give me the answer. Which of these is an open system? Answer. Nishu, Radhika, Prerna. Answer. I want the answer to this question. Great. Yes. The answer is all of these. Yes, it is all of these. The human body, it's a living organism. A living organism is always an open system. The earth is also losing the matter, and the matter is also flowing in the earth from the universe. And then we have the pond. A pond, the water is going to get evaporated from a pond. The rainfall is going to go into the pond. The mass is going to keep on changing with the seasons. The animals living in the pond, they are going to exchange the energy and the matter with the surroundings, and so on. Pond is an open system. Clear? Okay. Now we have homogeneous and heterogeneous systems. This is the classification on the basis of the appearance of the system, the phases of the system. A system is said to be homogeneous. Now this homogeneous and heterogeneous system we are going to deal again in the chapter called equilibrium, but here it becomes very important. The homogeneous system, when it is completely uniform throughout, we are not able to distinguish between the components. One part of the system is identical to the other part of the system. So, and please remember, whenever we are talking about thermodynamics, we are talking about intrinsic, extrinsic properties, we are talking about homogeneous systems. Clear? If it is heterogeneous, then in that case the properties are going to change within the system itself. So here we are talking about homogeneous system has only one phase. A system is said to be heterogeneous when it is not uniform throughout. A heterogeneous system consists of two or more phases. Homogeneous system basically are either one pure solid, or it could be the mixture of gases or the substance in solution. That is what we have as homogeneous system. Okay. Now we are going to talk about macroscopic properties. Well, whenever we are talking about any of the things in physical chemistry, we have to measure something. And the entire physical chemistry, if we talk about whether it be states of matter, whether it be solutions, whether it be kinetics, whether it be thermodynamics, whether it be surface chemistry, we are dealing with the measurable properties, measurable quantities. Measurable quantities we talk about, these are macroscopic system, macroscopic properties which are measurable by the instruments. So the properties associated with the macroscopic system that is consisting of large number of particles are called macroscopic properties. These properties are pressure, volume, temperature, composition, density, viscosity, surface tension, refractive index, and so many others. Internal energy, enthalpy, free energy change. These are all the macroscopic properties which are measurable by the macroscopic measuring instrument. We don't need to go into the infrared spectroscopy and so on. Fine. So these are what we call as macroscopic properties. Using these macroscopic properties, we define something called the state of the system. What is the state of the system? State is simply the current position of the system. But be very clear, you might have seen that, okay, you are going to give you, today's, whenever you are going somewhere, you share your live location. When you share your live location, at that time, the location is being shared by certain criteria, that is latitude, longitude, the positioning. So that is how we define the state, the position. Here, when we talk about the position of the system, there also we define certain certain macroscopic properties. And what are those certain macroscopic properties? These are temperature, pressure, volume, number of moles, density, the entire macroscopic properties. So when the macroscopic properties have a certain definite value, we define the state of the system. So our current position of the system is called the state of the system, the position of the system at which all its measurable property have a constant value is termed as the state of the system. So whenever we get the change has taken place, this becomes the state. Prerna, anything you want to ask? State of the system, is it very clear? The state of the system means the condition of existence of the system when its macroscopic properties have a definite value. Another word, same thing. If any of the macroscopic properties of the system changes, the state of the system is also said to change. Thus, the state of the system is fixed by its macroscopic properties. And these macroscopic properties, that is why, are termed as the state properties. So the state of the system is the condition in which the system is present. State is defined by measuring the observable properties of the system, the macroscopic properties. Now these macroscopic properties, that is why they are termed as state properties, state functions and state variables. The state functions, the values which depend only on the state of the system and they do not depend on how we reach that particular state. Like I said, initially itself I said that the person is wearing the trouser. How much time he took to wear the trouser, what the process he followed, I'm not bothered. I'm only bothered whether it is wearing the trouser or he's not wearing the trouser. So that is what we have as the final state of the system. Clear? Pressure, volume, temperature, so many variables. Now these are called state variables or state properties. State properties, the characteristics which are used to define the state of the system. These properties depend only on the state of the system and not on how that state has been achieved. You can find the change in the state properties by knowing the initial and the final state of the system. Like it's very easy to explain. Let us say we have a point A and we have a point B. An ant travels from point A to point B. Now, the ant takes the path. This is the path taken by the ant. This is the path taken by the ant. Clear? Now, this is the distance traveled by the ant. So, this is the distance. Now, you might be talking about what is the displacement. So, let's talk about the displacement as well. The ant moves from A to B. Now, this is the shortest distance between the 2 points in a specific direction. Now, this is what we call as the displacement. Distance is a path property. It depends on how the ant moves. Displacement is a state property. It does not depend on what the path you take. I just need to know the initial point and the final point and I know the displacement. So that is what we have as the path and the state property. So these are what we call as state properties, state variables. Clear? The variable, the value of which can be calculated from the state of the system itself is called a state variable. The change can easily be obtained, calculated by knowing the initial and final state only and without any information about the path of the reaction. So that is what we call as state variables. And then there are certain things called When a system changes from one state, that is initial state, to another state called the final state, there is invariably a change in one or more of the macroscopic properties. And that is why these properties are called state variables. Clear? So I believe all of you are going to be there in the session at 8:30 p.m. Just be there. Okay. Anybody who has not downloaded the Unacademy app as yet, go ahead and download the Unacademy app from the Play Store or the iStore and register yourself using the code AVLive. Okay. So that's what we have as state properties, state variables. Pressure, volume, temperature, mass, composition are the most important state variables. There are so many other state variables, but we don't need to define each and every of them. The values of the state variables depend on the final state of the system and not on how it has been reached. Is it clear? We are going to talk about, Anushka, we are going to talk about kind of state variables and properties. Okay. The variables whose values can be changed independently of each other are known as independent variables. Now, these are generally temperature and pressure. Volume depends on these two, hence volume becomes the dependent variable. Clear? Any confusions here? If the system is closed, mass doesn't remain a variable, mass becomes a constant in a closed system. And now it may be noted that for describing a system, it's not necessary to specify the values of all state variables. Basically, the state variables which have capacity to change in the given system, those are only defined. Clear, Prerna? Independent variables, like we can change the variables independent of each other. Like we have V is equal to nRT by P. Okay. Now, out of these three, I can change all the three, whatever value I want. I can put any moles, I can put any temperature, I can put any pressure. And depending on NTP, this V is going to have a certain value. So, volume becomes dependent on NT and P. So, NT and P become independent variable while volume becomes a dependent variable. Is it clear? Now, we have certain thing called state functions. State functions are also state properties. NCERT does not distinguish between state function and state variable. NCERT says state functions / state variables. But still there is a slight difference between them. State functions are the properties which cannot actually be measured from the system. Rather, they need to be measured by using other state variables. Something like the entropy. Now, entropy cannot be measured as such. Entropy needs to be measured by knowing temperature, knowing pressure, knowing the system. So, entropy is not directly measured. I don't have any instrument which is capable of measuring the entropy directly. Clear? So, that becomes a state function. Like state variables, the value of state functions also depends only on the state of the system. So, these are also state properties. They are independent of the path or manner by which the state is reached. Clear? The change in the value of these properties, state function, depends only upon the initial and final states of the system. Some common state functions are pressure, volume, temperature. That is, state variables can always be defined as state functions. And there are certain state functions which cannot be called as state variables. Now, we talk about the types of state properties. That is, extrinsic or extensive properties. So, Anushka, your answer, extensive or extrinsic properties. The properties, the value of which depends upon the size of the sample. Let us say I have some water in this container. Then there are certain properties which are going to depend on amount of water, like volume, like mass, like moles. So, mass, volume, moles, they are going to depend on the amount of the sample I take. If I take a drop, then in that case, this is going to be different. If I take the entire glass full of water, it's going to be different. So, that is what we have as the extrinsic or extensive properties. It depends upon the amount of the substances present in the system. The examples are mass, volume, heat capacity, enthalpy, entropy, free energy, length, and energy. Wow, length. Yes, length is an extrinsic property, isn't it? And then we have intrinsic or intensive properties. The property is the value of which remains constant irrespective of the size. It does not depend on the size, but it does depend on other factors. It does depend on the other intrinsic properties. Like we can talk about the density. Density is an intrinsic property, but it will depend on temperature. It will depend on pressure. Density does not depend on volume. Clear? But it depends on temperature and pressure. So it depends on other intrinsic property. Fine. Now, intrinsic or intensive properties, these change only when other intrinsic properties are changed. It's independent of the amount of the substance present in the system. You can take a small sample, you can take a large sample, something like density of water. Density of water does not depend on how much water we are taking. Prerna, what do you exactly want to know? You want to know independent variables, you want to know intrinsic property, you want to know extrinsic property? Tell me, I'll explain it again. So here we have intrinsic properties. The intrinsic properties do not depend on the size of the sample. Something like, let us say we talk about the refractive index of glass. Now, refractive index of glass does not depend on what size the glass slab you are talking about. Clear? Something like the concentration, molarity, molality, mole fraction. It does not depend on how much sample size you are going to take. You take a drop of it, you take a liter of it, you take a whole container, the concentration remains the same. That is the intrinsic property. Okay? The examples are temperature, density, concentration, viscosity, refractive index, surface tension, pressure, molar volume. Remember, not volume, molar volume. Gas constant, vapor pressure, specific gravity, dielectric constant, EMF of a dry cell, and specific heat. Heat capacity nahi, specific heat. Does change in state function is state function? It depends what we are talking about. We are talking about 0 to something, then it becomes a state function. Okay? Intrinsic property, I believe, Prerna, I have just explained it to you. Great. So that's what we have as intrinsic property. So we have intensive and extensive property. These are what we have as macroscopic property. Could you please tell me which of the following properties will change when the given solution is transferred from the beaker to the test tube? So I have taken the solution, I have transferred to the test tubes. So which of these properties is going to change? Concentration, number of moles, density, volume. The properties which change are extrinsic properties. The properties which do not change are intrinsic property. Clear? Concentration, no, it will not change. So it is intrinsic. Number of moles, of course, these test tubes, they are going to have different number of moles. Each test tube has different number of moles. So this is going to change. So this is extrinsic. Density, no, it's not going to change. This is intrinsic. Volume, yes, the test tubes have different volume. That is an extrinsic property. So this is going to change for the each test tube, and so it is extrinsic property. Is this clear? So intensive are independent of the mass or the size of the system. Extensive are dependent on the mass or size of the system. So that is what we have as the classification. Clear? And now we talk about one very important quantity. Very, very important quantity. And that quantity is called internal energy. Internal energy simply is the energy content of an object or a body. Clear? Now, this internal energy is not just one energy, it is actually a collection of many types of energy, different types of energy. That is what we have as the internal energy. One thing you need to be very clear, the exact value of internal energy cannot be determined. Absolute value of internal energy cannot be determined. The reason is not about instruments, like we don't have an accurate instrument or so. The reason is quite simple. Many of the components of internal energy are relative. Let us say we have potential energy, the energy because of height. Now, that height needs to be with certain reference. If you change that reference, the value is going to change. So, how are you going to talk about the total energy when one of the component does not have a fixed value? A component is relative. So, many of the internal energy components are relative, and that is why the exact value of internal energy cannot be determined. Yes, we can find out the change in internal energy. We have one particular state, we take that internal energy arbitrarily certain value, most often 0, and then we talk about this state and we talk about the change in internal energy. Is this clear? So, that is what we have as the change in internal energy. Okay? Clear? Now, this internal energy includes all types of energy. Molecules consisting the given mass of matter, such as translational, vibrational, rotational, kinetic and potential energy of the nuclei, electrons within the individual molecules and the manner in which the molecules are linked together. You name any energy and that's a part of internal energy. Clear? And depending on how the internal energy is changing, what are the various changes taking place, the processes are defined. Okay? Those who have not liked the session, go ahead and like it. I know there are not lot many people, but still, whoever are there, they need to like the session. So, there are various components of these internal energy. Like we have the components mass, nuclear binding energy, electronic energy, bond energy, vibrational energy, rotational energy, translational energy. Mass, it becomes a variable only for an open system. For rest of the cases, mass is a constant. Open system, mass becomes a variable. Nuclear binding energy, that is for the nuclear process. And what are nuclear process? Nuclear process is radioactivity. Nuclear fusion, nuclear fission. So, these are the processes where nuclear binding energy is changing. If the process is not any of these, then in that case nuclear binding energy is a constant. Forget it. Clear? Next, electronic energy. Electronic energy is when the electrons show a transition, when the electrons move from one position to another. That is something like a spectra. Or we are talking about the ionization, we are talking about the movement of electrons. So, that is what we have as electronic energy. Otherwise, electronic energy remains a constant. Bond energy. Whenever there is a change in bond energy, it is what we call as the chemical process. Any of the chemical process, there is a change in bond energy. Some little bit more small. The bond energy always changes whenever we have a chemical process. Now, for a physical process, the only change which is allowed, mass change, it's not a physical process. Nuclear binding energy change, it's not a physical process. Electronic energy change, it's not a physical process. Bond energy change, it's not a physical process. But when there is a change in vibrational, rotational or translational energy, that is the change in average kinetic energy. This is the only change which is allowed in a physical process. I'm not saying that in every physical process these have to change. I'm saying that these are what we allow in a physical process. Prerna, in physical process, bond energy remains a constant. In a chemical process, the bond energy is changing. Is it clear? Like we talk about boiling of water, the hydrogen bonds are being broken, energy is being absorbed. So boiling of water, as far as thermodynamics is concerned, is not a physical process, it's a chemical process. Okay? For a physical process in thermodynamics, the only thing which can change is temperature. Nothing else should change. Okay? Clear? And if you keep the temperature constant, in a physical process, there is no change in energy. Am I clear? In a physical process, at a constant temperature, there is no change in internal energy. Okay? So it depends on temperature. Any kind of doubts? Now we have something called path dependent functions. The functions, the value of which can be determined only if the condition under which the process are taken is known. Something like when you talk about the path dependent function, it's something like what is the distance traveled? What is the path you followed? So that becomes a path dependent function. How much time you took to reach from one place to another? Path dependent. Okay? How you did it. So that is what we have as path dependent function. Two functions are used in thermodynamics. One is called heat and other one is called work. How much heat exchange is taking place and how much work is being done, that becomes dependent on path. Any doubts? So path function depends on the path by which the system has achieved a particular state, can't have any definite particular value in any particular state of the system. Because again, the way you reach it, that's going to change the state. The heat and work, that becomes path. So that's the difference between them. State function is independent of the path taken. Path function is dependent on the path taken. Depends only upon the state of the system. Path function depends upon how that state of the system has been achieved. All paths result in the same value. The different paths may result in different values. Internal energy, enthalpy, entropy, temperature, pressure, volume, refractive index, heat and work. Okay. Now, which of the following is not a state function? That is, which of these is a path function? I have just told you the answer. Quickly give me the answer. The answer is heat. Q. Q is the representation of heat. We have 2 p.m. Botany class with Swati Batra ma'am. 3 p.m. we have Zoology class with Sachin Kapur sir. And 4 p.m. is chemistry session with me. So these are the sessions that we have. Join the Telegram channel for YouTube classes, t.me/NEET Elixir. And NEET UG subscription, iconic++, centers, that's what you can go. Use the code AVLive and join with our NEET UG. Download the Unacademy app, select your goal, put the code and use the subscription. Join with me. Here you are going to get the information about the special classes and the course that are being launched. Unacademy.com/Anoop Vashishtha. Follow me for free classes and the course. Okay. Download the Unacademy app and go ahead. Subscribe to the NEET Elixir by Unacademy for the best live classes. Like, share, subscribe and comment. Okay. Thank you. We are going to meet at 8:30 p.m. today in the session in which we are going to do the questions of surface chemistry. Clear? So don't forget, be there. Bye-bye. Take care.